Hi, everybody. Welcome to this ISEA webinar, the first of 2022. My name is Nathaniel Stevens. I am the treasurer of ISEA right now and also incoming president. I am here at the University of Waterloo and very excited to introduce this webinar to you. Our speaker is Dr. Jianjun Shi, who is the Caroline J. Stewart Chair and Professor at the Stewart School of Industrial and Systems Engineering at Georgia Tech. His research interests include the fusion of advanced statistical and domain knowledge to develop methodologies for modeling, monitoring, diagnosis, and control for complex manufacturing systems. Dr. Shi has an enormous list of awards and accolades that he's won. I would say two notable ones recently is that he was the 2022 Box medalist and the 2021 Schuhart medalist. He's also done a ton of service to our profession, including being the founding chairperson of the QSR, Quality Statistics and Reliability section of Informs, and that's what he's here to talk about primarily. ISEA and QSR overlap in terms of our interest area, and so we're really excited about an ongoing collaboration between us, ISEA, and QSR at Informs. And Dr. Shi is going to talk to us about QSR, and then also, time allowing, he'll also talk about some of his recent and ongoing research. So with that, I would like to, on behalf of everyone here, thank you, Jianjun Shi, for taking the time to speak with us today, and go ahead whenever you're ready.
Okay, thank you. Thank you for the introduction. It's really an honor to come here to introduce QSR sections of Informs, and also have an opportunity to talk about some of my research. So I have two separate presentations. First, I will introduce QSR, and then talk about my research. So I'd like to give an overview of QSR of Informs because there's a strong motivation from QSR Council to collaborate with ISEA Society, and believe we can work together, collaboration, to make a bigger impact to the society. So in this introduction, I talk about the history of QSR section and the membership structure, some major impacts, activities, and propose some ideas for discussion. How can we collaborate between QSR and the ISEA? So first, I say a few words about Informs. So Informs stands for Institute of Operations Research and Management Science. It's a leading organization on operations research and analytics. It has about 12,000 members and founded in 1995. So Informs covers probably all aspects of operations research analytics, mainly in industrial and system engineering in College of Engineering, and also business school faculty members at Informs. So Informs covers almost all ISE department research activities except quality reliability statistics until we form this section. Because QSR was not part of the initial formulation of Informs, the faculty members in QSR research area get kind of a no home in this major society. So when the QSR faculty members come to Informs, they go to contribute session and they don't have like a core activities, and also not very sustainable. So we believe in some time, I say 1996, I joined faculty to ISE 1995. So after realizing this, we talked with a few key members, say maybe there's a need of QSR because we have a QSR in different homes, quality, statistics, reliability, different societies. However, there's a need to link with operations research, management science, and also especially in industrial engineering and system engineering departments. There are faculty members here, and we need to be collaborate with others and recognized as one important discipline. That's why we initiate this QSR efforts. So in the very beginning, when we work on this one, we means the team try to formalize the society, talk to different professional societies related to QSR, different major conference related to QSR, and also the editor-in-chief of different journals. We say we want to formalize the QSR section, at Informs. Honestly, we get a lot of resistance. People say, oh, we already have QSR in here and there, so many societies, so many conferences. Why we need a new one? I mean, this is just one more. But with all efforts, we talk with different owners of different society, we convince them the industrial engineering is an important discipline, and the QSR, quality strategic reliability here, is a very important components to work on QSR, but also linked with the industrial engineering, the real applications, and also linked with optimization, management science. So from another domain, we expand the territory of quality strategic reliability. So under those kind of objectives, we get strong support from all bodies. I mean, the professional societies, the presidents, the council of others, the journal editors, and also the funding agency. We see the QSR can define some new types of research, not conventional QSR people doing. So after we have this initial success, we also need to demonstrate the QSR can sustain 18 forms. So in 1996, 1997, each year, the Inform has a spring and a fall conference in that time. So in each conference, we organize contributed cluster of QSR. So basically, the cluster is growing from 3 sessions to 10 sessions over the years. I mean, within these 2 years. So we convinced the board of Informs this is the sustainable section. So we wrote the proposal, and finally, the QSR section get approved 1998. So even approved in 1998, really the efforts start with 96, 97, or 2 years efforts. So those are the founding officers in 1998. You can see probably many familiar names. I was the chairperson of QSR, and Coxie was chair-elect, and the council member for the first one. And also we formalized a founding member advisory board. Susan Arbin was the chair, and those faculty members, you can see all senior faculty members from different societies, different editor-in-chief, and also some like NSF panel, NSF program director in this area, Larry Seifert. So those are very powerful advisory board and very energetic officers. And this is the photo after the QSR cluster. I'm here. You can see much younger at that time, all black hair at that time. So QSR membership, we have about 300 members, very stable over the years. And more than 50% are regular members. That means PhD working members. And slightly less than 50% graduate student members. Most of them are PhD students. And 85% of the regular member from academia, and about 15% from industry and the government. So you can see these are very dominant academic person involved. I say 75% of QSR members are very active in the professional society, the research, education activities, conference, editorial board, and so on. And the QSR members generate the best research outcomes in the related research areas. Most of, I say, all of these members are very productive with high productivity and high quality in research. So the major activities of QSR, each year, Informs has a annual conference in October, late October, early November time period. And QSR has been organizing the most number of sessions in the Informs section. In the past, I would say 15 years, we're always the #1 number of sessions. And also start from last year, 2 years ago, we have a QSR workshop. That's one-day workshop before the Inform conference. This is focused with QSR. So we have a dedicated time for QSR members to interact, not interfere with other activities during the annual conference. And we have QSR webinars, invited people from academia industry to talk on the frontiers of the research. And have a different best paper and poster computations in the QSR section. And also we have a data challenge computation. Basically, we get some real data set from industry, and then based on the design formula and the students, the faculty student team can analyze this data and compete, present the results. And this is the similar activity with the industrial data analytics case study. Also, QSR plan to, I say plan to means not yet, want to QSR related international conference, or even have a QSR sponsored conference. QSR organized like virtual happy hours and have interactions, and during the virtual happy hours discuss some topics the QSR member interested. And also QSR provide network capabilities at the informs like reception, and people support each other, get to know each other, and also mentor new members from senior members. This is one example of your QSR cluster in 2021. And over there, also they have about 50 sessions and some special sessions like joint sessions with different sections it informs. So people from different sections can interact, communicate, and have different computation, best paper, best student paper, poster, industry data challenge. So it's a computation. And also develop have different panel discussions. For example, how to write SBIR, STTR grants. We have industry and also university person to jointly write SBIR, STTR, share the experience, and invite the program directors from different federal agencies to give panel to explain what's SBIR, STTR. And how to have startup companies for start kind of discussion and focus topics on different topics. And also for graduate students, junior faculty, we have an editors panel talking about the publication requirements. And another nice one is the student introduction and the interaction sessions. This one has been doing for, I don't know, probably 8-9 years for this activity. Basically, relatively senior PhD students get together in a session. Each person talk about 3 minutes about their research, what they are doing, what they plan to do. And the nice part is the students get to know each other, and they can get a sustained friendship. And also the recruiters from industry, from academia can come here to see who is graduating, what kind of topics they are working on. And also during this session, immediately with the lunch and the poster session, those students will present their posters. So the recruiters can talk to them and have some active interactions. So that has been a very good experience from students, recruiters, and also faculty members. And also we have a journal sponsored session. Basically, the editor-in-chief select he or she believes the best paper to organize the session and present this one in the Informs conference. And also QSR continuously promote international collaborations. For example, MBIS co-sponsor sessions, and also co-sponsor session from Asia. This year, in fact, next month, QSR also organize sessions in MBIS annual conference in Norway. I will be there also next month. So those are the major activities. If you see what kind of words show up in the session titles, you can see the number one, I see the largest one probably is the data. So we have lots of data-oriented, analytics-oriented, something about learning, manufacturing, reliability, quality. Basically, you see these words, you can see the frequency. Those words show up in the session, and then you can see what are the hot topics in QSR. And also QSR not only doing theoretical research, but also focus on many different applications, such as advanced manufacturing, basic nano manufacturing, 3D printing, assembly, rolling, automotive, aerospace, different manufacturing process, complex dynamic manufacturing systems, bio-related research, healthcare, power, supply chain, energy. So those are the application areas, but we focus on quality, statistical, reliability issues in these applications. So talk about the impacts of the QSR activities. In USA, the NSF Career Awards is very prestigious for junior faculties. And we say all winners in QSR area, in this research area, are members of a QSR section in the past 25 years. And also many QSR members serve as editor-in-chief, editors, associate editors, and so on in the top, basically top journals related to QSR, like Technometrics, JQT, IC Transaction, QT, So those are, if you look at the editorial board, you can see lots of familiar names in the QSR community section. And also QSR organized competitions are one of the major sources for QSR related faculty recruiting in universities. I knew when QSR best paper competition, different competition, including student interactions, many department chairs from ISE come to that kind of session to check on as finalists. Most of them get a nice offer 1 year later. And also, more QSR members service different professional societies, like conference organizer, workshop organizers, and organizer, and so on. So basically, like I said earlier, very active members the QSR play in the society. So here list some ideas for potential collaboration between QSR and the ISEA. I studied ISEA's website, and we found both QSR and ISEA share a very important common vision, which is a fusion of statistical methods with domain knowledge to solve challenging real problems. So this is true for both QSR and the ISEA as a society. And also, we feel QSR has the most strength in academic research, and the ISEA is very strong in understanding the needs and the challenges in real problems. So we work together, probably can generate more frontier important research results and make a real impact and motivated by real problems. So in near term, we can consider QSR and the ISEA can jointly promote some new frontiers research topics and their applications. So the problem, the data is really rooted from the real engineering problems. And also exchange some new ideas and develop collaborative efforts. And also improve communication between industry and academia through that kind of joint efforts. And there are a few action items we can consider. One is jointly sponsor webinars, workshops, conference, and the people from QSR and the people from ISEA can actively participate to get to know each other and get to know each other's strengths, capabilities. The ISEA members can participate in the QSR sessions at the Inform's annual meeting, and also QSR members can participate in the ISEA-sponsored conference. And also ISEA can provide case studies, associated data sets, also serve as referees and judges for industry data analytics computation in QSR organized events. And I talked with people from industry, like leading data scientist, data scientists or managers manage the real problem-solving data analysis. They think they believe the data computation in QSR is a very good experience for them. For them, they have real problems and they have real data. If they can desensitize the data, make it a little more generic, can be publicly analyzed. The data and the problem can be open to almost all top universities and all the researchers, graduate students, and they can provide solutions for these types of data, which go much beyond the capability of the industry data scientist group, because they have a daily, they have daily activities, responsibilities, and also very limited human resources. But with this data open to the like a QSR society, they can get lots of solutions, options. And also the QSR council had faculty members delegated, work with industry members to get some initial study on the data and try to define the evaluation, give some guidelines. So this one become, I'd say, for industry, can get lots of ideas, try out with minimal investment. The investment really means you need to get the real data, desensitize it, and most of the time you can give like a few $1,000, $1,000, $2,000 to give the winners. So that kind of activities could be very good for both industry members and student training and potential research. Another thing I'd like to mention is the international conference on the interface between engineering and statistics. This is the efforts initiated by Professor Jeff Wu and me. So in 2007, Jeff and I got together with Jeff, of course, is the leading scholar in statistics, industry statistics. Myself is more like an engineer. So we say the statistics expert and the engineer may work together to identify some problems, present the result, and promote some kind of research. So we propose to have this conference, international conference on interface between statistics and engineering. So this conference has been like every other year we organize it. It's 5 times since 2007 in China, Taiwan, China again, Italy, South Korea. South Korea is 2019 because of COVID. There's no activities on this conference again. Each conference had about 150, 180 attendees for about 3 days activity. About half from a statistical community and half attendees from engineering community. And all the paper topics, presentations, discussions focus on the interface. So we emphasize the interface or synergy between these 2 communities. If you click this link, you can see all the activities for the 2019 conference. So Jennifer will have the slides. So feel free to post this one in your website. If people are interested, you can find out. So I mentioned this one is think about maybe QSR and the ISEA can jointly sponsor this conference. And I talked with Professor Cox-Hui at Virginia Tech. Professor Cox-Hui had been either chair or co-chair of all those 5 previous conferences. And he is very experienced and knowledgeable, and also knew the people how to organize conference. So if QSR or ICA like to follow up on this one, feel free to contact Cox-Hui. He's willing to help. So those are my introduction for QSR and potential ideas for collaboration. We have Mustafa and Arman from QSR section. They are from the QSR Council. Both of them will be leading the efforts, have a follow-up discussions with ISEA to see how can we do better in this collaboration. And hopefully QSR, like more from academia, and ISEA, like more from industry, we can be strong partners to work together in the years to come. Okay, I will use another 20 minutes also, briefly introduce another topic. If you have questions, please put into chat, and we will have time to discuss those topics.
Yeah, while you get that second presentation set up, I will remind the viewers here that there are two boxes, one for chat, one for questions. Use the question box to input your questions, and I will moderate those and keep track of them. And as John just said, we'll be able to have time for a discussion at the end. So if you've got questions, please use the question box.
Okay, thank you. So I'd like to have some brief discussions on this in-process quality improvements, the concepts, methodology, and applications. And with exactly the same name, the ISE transactions has accepted paper, which is the link here. If you click this one, that's leading to the newly accepted paper on the same topic. Over there, it's a long paper, have lots of discussions on the ideas, concepts, different applications, different methodologies, and so on. In this brief discussion, I will talk about the concepts of IPQI, and I give some examples. I only talk about the problems, not the solutions in this discussion because of time limits. And if we have time, I'll talk about some future IPQI research opportunities. So where does IPQI come from? It's from my interview talk with IOE, Industrial Operations Engineering Department at the University of Michigan. So in 1995, I'm invited for a faculty interview and to join the faculty, and they told me I will be in quality group in the IOE. My own training is from EE automation, bachelor, master, PhD in China in automation, and PhD in manufacturing in ME department, University of Michigan. So I really don't know much about the ISE and also the quality. So I studied the problem. I say, here's the manufacturing process. We have the product process design, manufacturing process fabrication, product measurements, and then ship to the customer. And talk about the existing quality methodologies. We have design experiments with efforts to design the product process robust to the disturbance. We have an ISPC, accepted sampling, to check on the product, how good it is. And also, that means quality management, which covers all the management aspects of the process. By looking at this existing methodology and also manufacturing system, I see there's an opportunity in manufacturing process. In other words, in the manufacturing process, we have lots of thinking, lots of data, and by analyze this data, we can have the quality improvements in different aspects. So I wrote a proposal based on this idea. I got the ISEA Career Award next year. So compare with the IPQI and the conventional ISPC, what are the difference? So we think about the major tasks in quality improvements. The process faults. ISPC emphasizes detection, but the IPQI try to emphasize not only detection, but isolation and find out what are the root causes systematically. And talking about the product defects, ISPC talk about inspection, but IPQI emphasize prevention. So we try to do something in process, so defect will not occur. Try to talk problem solving. So ISPC emphasize process change detection, but rely on operator to find out what are the root causes, how to solve the problem. And IPQI try to propose a systematic approach. So when we say a systematic approach, it shows this. Again, this manufacturing process here, and ISPC, based on the product measurements, depend on the people, close the loop. For IPQI here, we not only based on the product measurements, but also based on in-process sensing data. Based on the data analysis driven by engineering model and optimization, system theory, control theory, we can systematically find out what are the root causes, how to do the compensation, and close the loop. So this is IPQI. In order to do an excellent job in IPQI, we need 3 pillars. One is engineering domain knowledge. Another one is the data science. Is not only statistics, but also computer science information knowledge, signal processing knowledge, and operations research and control theory. So these 3 pillars work together. We can make do a good job in IPQI. So here I take a few examples. In the very beginning, what's the motivation of IPQI and what's the current research frontiers of IPQI? So this is, I put the year there. This was a project I've been working on in the early 90s. So which is the signature analysis for stamping. In stamping industry, before we talk about IPQI, how to do quality control, they get the stamped product, check the dimension, check the size, check the surface, and check the product, basically to say if this product meet the engineering specification or not. If not, the technician go back to check out what the problems, the die problem, die setup problem, price problem. Basically, there are more than 40 different variables, which may leading to defective parts, which are time consuming. And also, for 1 hour, they can produce like 500 parts. 500 parts could be per minute, very high production rate. But the checking, how many parts inspected, is very, very few. So from another aspect, we can see in the stamping press, there are lots of sensors: shot height, punch speed, tonnage, vibration, temperature, and so on. So all those sensors collect the data for each part when we punch it. And each sensor generates lots of data. And also, this sensor reflects the interactions of the parts, the die, and the press. If we can analyze this kind of in-process sensing data and see if it's stable or some of sensor change in different patterns, we can predict the part quality, and also something wrong, we can find the root cause of the problem and also give suggestions how to quickly resolve the problem. As an example, this is the tonnage signal. This one is from the upper die going down. This one touch the bottom, and then the force increase. And then this one finished the forming the upper die, lower die departure. So you can see in this one cycle corresponding to one part, they have different segments. And each segment has the potential interactions, potential faults, and potential signal characteristics. So this one is, this information can be summarized as a domain knowledge with different segments corresponding to different angle. We have different potential faults, and we have potential different frequency and the time domain information. So with this knowledge, we can use wavelets analysis as an example to find the original signal corresponding to different segments, and then corresponding to different coefficients. Through this kind of mapping, we can monitor those coefficients in terms of key frequency, key time domain information. We can do product quality improvements. So this one is an example for IPQI, in-process sensing data fusion to predict quality, find the root cause, and improve quality. So right now, quickly say, time goes to 2018. I got contact from a major semiconductor company, and they told me this problem. In a chamber, they have a wafer manufacturing. In a chamber, they have 130 sensors in this one. And these 130 sensors for each wafer, they generate lots of functional curves like this. And for each functional curve, they get multiple steps, like a different deposition, different cleaning tasks. And this one within here, they have as example, 24 steps. And these 24 steps, each step they do different tasks. Because of a feedback control in the within built-in chamber, this how long this step 1 switch step 2 is changing. It's not fixed, not like after 20 milliseconds the step 1 ends. Could be 18, could be 25. That's one thing. Another thing is when they're doing different tasks, different groups of sensors are correlated cluster. When they shift to another task, another cluster of data related. So this one give a challenge to do multivariate, multifunctional curve monitoring. Because if you don't know when the step change, which cluster and which sensor function curve, which function curve interrelated, you cannot do a good job using multivariate techniques. So we need to have the automatic segmentation and automatic clustering. So basically, we have this functional data, and this data has different segments. When they segment the segments, the boundary is changing. And within each segment, we have different clusters. So if we can do both of this, and then we can do for each cluster, we can do a feature extraction and so on. But if we cannot have these two red color done correctly, we cannot do a good job for in-process sensing data quality improvements. So we did this one. Basically, we developed method. You can see the paper over there. We can detect. We cannot use the semiconductor data to write paper, so we use this data set, people movements, to study. So go back to the semiconductor manufacturing. After you get the automatic segmentation, automatic clustering, for each cluster, we can have the monitor. We use a functional PCA, multivariate functional PCA, to monitor the statistics. And we have multiple clusters. And how can we determine if a chamber is a good condition or bad condition? We use this top R decision statistics. I like this very much because we have multiple clusters, each cluster corresponding to a statistic QI. And we found the largest R QI, make a summation, and use this one as a decision for the whole system. If the system is good, not good. If our system is very good, we don't have significant larger ones, this WI will be in control. If not, this will be out of control. Because we focus on top R, largest ones, we always focus on the worst cases of the system. Oh, this one get ASQ. This is a nice award. Okay, another thing we have been working on is physics-driven machine learning for multi-stage manufacturing process. So this also motivated by real problems of a rolling process. In a rolling process, they have 50, 80 roller stations. Each station has about 15 typical variables: roller speed, temperature, coolant, and so on. So there are heterogeneous data in that kind of system, and how to find the interrelationship, especially the causal relationship, to do forecasting and control and root cause diagnosis. When we say physical-driven machine learning, because for the rolling process, we know the physical layout, which one roller station first, which second, how they interrelated, how the rolling bar goes through this. And also, we know what is the material property for each stage, what are the process variables, what are the quality variables. Before I run the production, I get the observational data. I kind of know how they related, how they could be related, because I'm an engineer, I know the physical causal relationship. But I don't know exactly the number. So with that kind of a structure, get from the engineering and the real production data to model this one, I can use much less production data to get a much more reliable causal network. So this is another work we have been doing. Oh, sorry, that's terrible. Okay. So let's skip this one. We also do some nano-bucky paper problems. We also do high-dimensional streaming data monitoring diagnosis problems. So for this high-dimensional streaming data, this one is data from the wafer manufacturing semiconductor. This one is from a composite parts inspection. This one is from a rolling process, high-speed video signals. So those are the defects in this image here. So the problem the challenge we have is a high dimension problems, high velocity. This one for this speed is 400 feet per second, the speed of the roller bar. It's complex spatial temporal structures. And also we don't know when this fault occur, what kind of shape, where's the location, and so on. So because of those challenges, we develop an unsupervised feature extraction method from this high dimensional data for root cause diagnosis. Why unsupervised feature extraction? Because the labeling is very expensive, and also process data is very cheap, and also we cannot get all this possible shape location information. The way we do it is doing this for height streaming data. We do the one-step decomposition from the profile data decomposed into smooth background, sparse, anomaly, and noise. And we formalize to this optimization problem, and also design algorithm can quickly solve that kind of optimization problem. And this example for the rolling, I mean, this real-time image background anomaly once it's occurred, and this one has the alarm to have this happen. And also we expand the method to have adaptive sampling, so not 100% data, but some purposely sample data. And we implement this one with Boyne's inspection, composite parts inspection. So for the method used in the industry practice, they need 2 hours to inspect 1 square meters composite parts to get this detection. Use our method, adaptive sampling, we get 300 points, 2 minutes to get this defect detected. So that's quite significant improvements compared with current industry practice. I talking this one finish. So another thing I've been working on is the stream of variation methodologies for multi-stage manufacturing process. So for multi-stage manufacturing process, almost all manufacturing multi-stage, you can see 150 parts, sampled parts, through about 100 assembly station become a body in white. So each assembly station is 1 stage, and then they have propagation. The engine had 24 machining stations to get this. 3D printing layer by layer is also multi-stage manufacturing to get the final product. For multi-stage manufacturing process, there are several challenges. One is that there is a variation propagation. So something wrong in 1 stage, this sub-assembly will be wrong and eventually show up in the final product. There's a tolerance synthesis problem. I want certain tolerance in the final product. How to allocate tolerance for each part in each stage and also tooling. Root cause diagnosis. If something wrong in the final one station, we show up in the final one. But how can we find out which station, which part gives this problem? Distributed sensing. So in multi-stage, 100 stations, in which station measure which feature makes the whole process diagnosable. If something wrong, I can find the root cause. Critical station identification. So there are hundreds of stations. There must be some station more important than others. How to identify which one? Automatic compensation. If I do assembly in this stage, these parts already have some dimensional error. What I can do in the station to compensate that kind of error when I assemble parts together to make the defects not so bad or within tolerance. So this automatic compensation problem. So for all those kind of challenges, we can formulate this problem as a state space model. So for a given stage, I have a quality already made in the early stage. And within this one, after this one, I have quality vectors. Within the stage, I do something on the parts, which is the UK tooling. I have a natural tolerance noise, or some fault occur in this one, impact on quality. So I model this one as a state space model like this. A, B, product process design information. And also within stage, I may put a sensor there to measure the quality features. So YK is measure the quality through the CK. So if you're familiar with the linear system or system theory, this one is just a system theory problem. However, the fundamental difference is K. In control theory, K is time, is from 0 to infinity. In multi-stage manufacturing, K is a stage, it's always a limited number. So because of this, there are lots of fundamental research on the controllability, stability, sensitivity, and so on. So we, through this kind of a model, we link the control theory, the multivariate statistics with multivariate process control. And also, through this kind of methodologies, we can use this one to do the system design evaluation, tolerancing, sensor placement, diagnosticability, fault diagnosis, quality reliability interactions. When we work on those kind of problems, we not only develop a theory like in the book, but also work with the company, with a DCS, to develop commercial software like a SOA, Stream of Variation Analyzer. And SOA has been used widely in almost all automotive industry and also aerospace, or in Lockheed Martin, Airbus, for their variation analysis applications. Just one more project, I've been working on it for 6 years, is machine learning enabled composite parts assembly. So this one focuses on the fuselage. This airplane, the middle cylinders here is fuselage. So for Boeing 787, they have major problems in the fuselage assembly. When they put two pieces together, there's a gap. And this one really slow down the assembly process. So we proposed a control strategy. Basically, for incoming fuselage, we measure the dimension, and after we know the dimension, we use actuators like this one, push and pull, this one, so we can adjust these two fuselage to make them match to each other, and then we can do the assembly. So this is the basic idea. But in order to do this, there are lots of challenges. And here I just say one. When we have the fuselage coming in, each fuselage is not perfect. It's like an arbitrary shape, like a cylinder, but never perfect. So in this situation, where to put these actuators, put in which position, we can use less number of actuators with less force to deform the parts to adjust more efficiently. So this is a very challenging problem. And we use smart learning to solve this problem. Basically, our method can have a minimal deviation. So this one is that maximum deviation, smaller is better. This is our result. And this one is the force used to adjust. So you can see our force always the smallest one. And also the position, the red dot is the actuator position, is changing as the incoming fuselage dimension change. Okay. There are more discussions on the R&D opportunities, basically how to have data analysis, different machine learning techniques, how they help IPQI. And IPQI use the emerging manufacturing process, cybersecurity issues in smart manufacturing related to IPQI. So all those will have detailed discussions in the paper I just mentioned in RIC transactions. Anyone interested, always welcome to discuss with me. Okay, I stop here for the introduction. If there are any questions, I'll be happy to discuss.
All right, well, before questions, let me just, on behalf of everybody, thank you, Dr. Shi, for your time and your experience and a wonderful talk. Just a few comments. I'm really happy that you agree with us at ISEA that there's an opportunity here for collaborative sort of engagement in a synergistic way. The idea of sort of breaking down the barriers between academia and industry, which have traditionally been siloed, I think that's a really good sort of cause for us to strive toward. And for those of you attending, just to give you an idea of some upcoming events and initiatives to that end, the first was this webinar with Dr. Shi. We have our association's president, Peter Parker. He's giving a similar overview of ISEA in a QSR webinar later in the summer. I'll post the details about that at the end of our discussion here. We also have been invited by QSR at the next Informs meeting to be involved with a session showcasing ISEA case studies. So lots of interaction in that way, but I still think lots of work to do. So a few questions. Your work is a perfect example, I think, of being able to solve practical problems with sort of advanced research, advanced statistical methods. And you've got clearly a research group working on this. And one thing that we struggle with ISEA is to try to think about how to get students involved in this. And I'm wondering how, in your experience, has that gone? You know, how involved are the students in right from the beginning of problem formulation through to the very end when you're communicating an ultimate solution? If you could talk a little bit about how you've involved students and sort of the successes of that, that would be really helpful.
I think all research I've been doing is with my PhD students. My requirement for a PhD student, or my suggestion is students should have solid data analysis capabilities, like advanced statistics, machine learning, or algorithm, those kind of capabilities. All my PhD students get a master's degree either in computer science or statistics or computing or machine learning. So in addition, they get a PhD either in mechanical engineering or in industrial engineering. They also get a master's degree. So they have a solid training in other aspects. Another thing I ask students saying, if you work on a particular topic, you should be a domain expert, just like engineer work on that kind of problem. You should make efforts to learn this. If you're doing a semiconductor, you should learn semiconductor. If you do the rolling, you should understand what's the rolling. So this, I think that's a way to link the data analysis with the real applications. That's one thing. Another thing is emphasize the interface between engineering and statistics. That really is a point we can make. We means our students can make a contribution, because if you talk about people purely in machine learning statistics, they are lacking of engineering knowledge, the domain knowledge. If you're talking about the true expert in mechanical semiconductor manufacturing, they're not so skillful in the data analysis. But use data to solve the real problem is not necessarily take 2 courses, you can solve it. There are some inherent fundamental things need to fill the gap. And that gap will make the original contributions in both society. And that's really leading to the top research results. Yeah. Mm-hmm.
Yeah. Well, I think from my own perspective as being a student, you know, that kind of mindset, that kind of approach and philosophy to these sorts of collaborations, I think is really, really valuable. Speaking of collaboration, going back to your initial talk about QSR, you mentioned QSR interfaces with other Inform sections, and I wonder if you could talk a little bit about what sections you interface with, and what does that collaboration look like? What are the goals and what are the outcomes?
Within Informs, the closest one is the data mining. Right now, the society used to be a section. So data mining has the tools more focused on data mining, but also the QSR people also use data mining tools to solve quality reliability problem. So that kind of a collaboration for QSR people can learn more what's going on in machine learning and solve the QSR problem better. And also QSR collaborate with data, the analytics group. That's a very large group within Informs, because many data analysis problems in the QSR are interrelated. Recently, I say recently, probably past 5 years, they also interact with healthcare, because healthcare has a lot of data-driven analysis modeling problems. So I think basically is try to identify the strengths of another group and have joint sessions, joint collaborations, so the other group of people can learn what kind of tools, methodologies QSR section has, and also QSR sections can go over there to learn what kind of problems, how they formulate the problem, what kind of data available. I think in these aspects, that promote collaboration. The collaboration not only in the Informed conference, I would say that is the starting point, but as a follow-up, can have a joint proposals, co-supervise students, I mean, among the faculty members.
Yeah. So you touched on both in your response there and once in a slide, sort of the importance of collaboration with this thing called data science. And that's something that I think in the statistical engineering community, there are mixed feelings about sort of the value of data science and the opportunities and maybe the sort of negative side effects. And so I wonder, from your perspective at a high level, what impact does this broader view of data science have on things like industrial engineering, statistical engineering, quality problem solving?
I think it depends on how you think data science was covered. I believe, I know Jeff Wu coined this data science when he became a chair professor in University of Michigan. That's the first time he put this word there, and he think the statistician should be a data scientist in the future. I just say my view. My view of data science is for sure statistics is an important component, but beyond statistics, the computer science, the machine learning, the algorithm computing, those are all in an umbrella of data science. And under this, there are lots of potential impact in industry. I just, in one example, this semiconductor company, this 130 sensors, if we cannot solve the segmentation problem, we cannot solve the self-automatic clustering problem, we cannot use multivariate methods to solve this important problem. In fact, I know the semiconductor in, I would say, Intel, in Texas Instruments, in Taiwan, that's and also Samsung. They all put lots of money to do the multivariate monitoring for these functional curves for the semiconductor. None of them successful. They started to do this one 2006, I believe. Even today, before we work on this topic, the industry practice is for each functional curve, they put plus minus 3 sigma, like a dashed line above and lower. If a functional curve trigger go beyond this one, they count as a point. If how many curves trigger this one, the points increase. And then beyond certain number, they send alarms for this. That's not very good. We compared our methods. After we have this auto segmentation, auto clustering, and also I say top R method. This one is much better. I cannot say the number, but much better than the conventional one. I say this is a good example of data science solve the real problem.
Yeah. I see that we're at 1 o'clock now. There's 1 or 2 other questions here that we didn't get a chance to get to, but I think to respect everyone's time, we'll end it here. And I'll invite if people do have other questions they want to ask you directly. I'm sure they can email you if they'd like. So first of all, let me thank you again on behalf of everybody for a wonderful talk and for sharing your time with us. And I want to thank everybody who tuned in live and who may later watch this recording for your attention and your participation.